Okay, so in this video, we're going to look at how to turn a curvy graph straight, which is a little bit like cracking an egg with a sledgehammer, the technique that we're going to use. So to start off with, set up your experiment and collect some data. We're going to do all the usual things like multiples and dividing and repeating and averaging. Imagine you're swinging a pendulum and seeing how its period depends on its length. Set up your results table the way you usually would and then calculate the average using the standard technique. You can see it there in red. When we're doing these experiments, we have to carry the uncertainty right the way through from our experiment, through our results and our processing, and into our graph. So we're going to have to drag that uncertainty through the repeating and averaging. And to do that, we're going to calculate the difference between the average value and the value that's most different from it. Then what we've got to do is round that uncertainty up to one significant figure. We can't justify having an uncertainty of more than one significant figure, and to make sure we account for the worst possible scenario, we always round the uncertainty up. The next thing after that is to round our average so that it matches the same place value as the uncertainty. So in this case, our uncertainty is 2dp, and so we have to round that average from 7.157, just rounding normally, not up, rounding normally to 7.16. Now, because our original experiment used accuracy improving techniques like multiples and dividing, we timed 10 swings. Now we have to divide by 10. And that's really cool because this allows us to see that as we divide the average by 10, we also divide the uncertainty by 10, which reminds us that multiples and dividing increases the accuracy by decreasing the uncertainty. When we're using this technique, there is no need to plot a curvy graph. We just assume that the data is going to be curvy, but if we did plot up the data from a pendulum, changing its length and measuring its period, it'd look something like that. And so if we chose to draw a best fit line, our best fit line might look something like that. Once again, we don't have to do that. And if we were wondering what sort of relationship our curvy graph showed, the one that we don't have to draw, we might think that it shows a square root relationship, x to the power of a half. So we're just going to take a pause now in our experimenting and graphing and results table and have a look at the theory for this log-log technique. This log-log technique, natural log, or log base 10, assumes that your raw data has the form y equals some number a, x to the power of some other number, n. We're going to take that equation to pieces a little bit. We're going to take logs of each side. And you can see that I'm choosing to use the natural log. That's the ln button on your calculator or on your spreadsheet. Then using the rules of logs, we can split that log of ax to the n into the log of a plus the log of x to the power of n. It's that rule of log fg is the same as log f plus log g, you might remember from maths class. Then we are going to split that log of x to the power of n into n log x, and I've just rewritten the equation down on that bottom line there, log y equals n log x plus log a, we're going to compare that with the equation for a straight line graph and see what similarities we can spot. Wow, look at that. Those are so similar. If we log both sets of our independent and dependent variable and then plot them up, they're going to make a straight line graph. And the gradient of that straight line graph is the same as the power n. The y-intercept of that straight line graph is the same as the log of a, that some number in y equals ax to the power of n. So keeping that in mind, we're going to go back and set up a new results table for our process data. And you can see that in the first column there, I've got log of length in meters. So my first length was 0.13. I've just taken the natural log of 0.13, which was 2.04. And so I've written that down. How to round the logged values is a bit interesting. It's worth talking about. If we look at that original value that we've logged, the 0.13, that's two significant figures. But my logged value, 2.04, that's three significant figures. It's 2dp though. And so whatever significant figures we start off with, we have the same decimal places on our logged value. Just take a moment to let the significance of that settle in. Next, we have to do the uncertainties, and the way we do that is taking the log of the maximum possible value. Our uncertainty there in length was 0.01 and the length was 0.13, so we can add those together to get the maximum value of 0.14. You can see I've logged it there and got negative 1.97. The next step is to do the same, but for the minimum value. And so this time I've minused off the 0.01 to get 0.12. And the log of 0.12 has given me negative 2.12. Interestingly, the log of any number less than between 0 and 1 is negative, and the log of any number above 1 is positive. Next thing, we're going to head over the other side and find first the log value of the average, and then we're going to do the maximum and minimum possible values for that average, which I found by adding on and subtracting off the 0.006 uncertainty. So you can see 0.722 and 0.710. Righto, having processed all of our data, now we're on to graphing it. When we graph it, we have to draw a full set of axes that includes both the positive and the negative numbers, because our log function can give out both positive and negative values. They probably won't form a perfectly straight line, but it should be roughly a straight line. Something like that, maybe. This year, though, when we're plotting, we're not just doing x's. We have to put error bars onto each data point, which come from our results table of those maximum and minimum values, and they put limits of how big or small each of those values could have been. And they're going to look something like that when we plot them on our graph. Drawing a line of best fit should be no trouble at all. And if everything's gone well, not like in this example, the line of best fit should be able to pass through the error bars of every single point. There should be no point that the theory fits that the line does not pass through. Then the way that we carry our uncertainty through onto our graph is by drawing an error line, which might look something like that. What the error line tries to do is draw the worst possible, worst plausible fit to the data. So a line that goes through lots of points and has a gradient and a y-intercept that's pretty different from the best fit. It's not the same as a line of worst fit. Thinking about it, a line of worst fit would be at right angles to all of that data. That would fit terribly. What it is it's the worst possible line of best fit, and we're going to use that to put some limits on the equation that we're going to write. We're going to use that to put the uncertainty into our equation. I'm hoping that all of us are going to go through this process on a spreadsheet, so this should be really easy. But what we need to do is for each of those two lines, we need a best fit and an error, gradient, and a y-intercept. And we're going to process that y-intercept data a little bit by anti-logging it. For natural log, that looks like e to the power of whatever that is. Wow, there's a lot going on here. First of all, have a look at where I've done that a equals e to the power of c up the top, taking the anti-log of the c values for both the best fit line and the error line. Then moving down from there, you can see I've calculated the uncertainties with those numbers. For the best fit line, the uncertainty in the m value, the gradient, is 0.06, and that already is one significant figure, so I don't need to round that. For the uncertainty in the a values, that was 0.0368092. I need to round that up to one significant figure because we can't justify having uncertainty of more than one significant figure. That's why that's rounded up to 0.04. Okay, so what we've got to do now is drag all of that data together and build an equation. And thinking back to our original experiment, we were swinging a pendulum backwards and forwards and measuring its period t and seeing what the effect of changing the length of that was. So our y value, our dependent variable, is the t, and our x value, our independent variable, the one we're changing, is the length of the pendulum. Looking at the power, like L to the power of what, that power comes from our gradient. That's the 0.51 plus or minus 0.06. Then, looking at the A value that came from anti-logging the y-intercepts, that's the 1.86 plus or minus 0.04.